Hello everyone, welcome back. We saw in the last class that when we use lax band drop or beam warming kind of a scheme, basically we get something called overshoot or undershoot, which creates wiggle, and these are therefore not total variation diminishing. TVD is an essential property for a scheme to have to basically to use those schemes in the problems where you have discontinuity like shocks or contact discontinuities, right. So, we need to control the slopes. So, we looked at different slopes, okay, upwind slope, downwind slope. So, when we are looking at the downwind slope, we got the lax band drop scheme. When we are taking the upwind slope for the linear reconstruction, we got the beam warming, and when we use the centered one slope for the linear reconstruction, we got the From's scheme, right. So, none of these schemes were working fine whenever we had the discontinuities. They are working very well in the smooth region, but in the discontinuous region, especially in strong discontinuity, sharp jumps, they were leading to, they were creating wiggles. Okay. So, the idea is to basically control the slope. We should use the slope which does not lead to overshoot or undershoot. So, this idea of limiting the slope is called the slope limiter. Okay. And one of the very natural thing to do in the slope limiter is basically use something called the minimum of the slope that you get from the left or the right, right. So, for example, you have 3 points like this, these are the cell centers, okay, okay, and you can get the slope from here and you can get the slope from here. Okay. Take the absolute slope, okay, and see which slope is higher, which slope is lower, and use that slope. That is what is the idea, and this kind of limiter is called the mean mode limiter. This is one of the most famous limiter because implementation is very easy. What you need to do is you need to calculate the slope here, okay, from I plus 1 at I, we call it the downwind slope S d, okay, and then you calculate from the upwind I and I minus 1, we call it S u, okay, and now we have to basically pick up the smallest one. And why we are doing that is because we do not want to create an overshoot or an undershoot, right. So, how does it work? What is mean mode? So, basically take the way it is defined. So, mean mode S d and S u. So, basically take the multiplication of these two, okay, S d S u. If it is greater than 0, then we will have either of this or that. If it is less than 0, then what is happening, that something is changing drastically, okay, or maybe you are at the valley or at a peak, right. So, maybe if you are at a peak, so you have slope coming from this side and this side, okay, and you basically what you want is your value should go to 0 here, okay, because if you try to use the value. So, what is this giving? This is giving me the slope, okay, on the peak or the valley. If you try to use a slope, what will happen is that it will create the artificial wiggles that we have discussed earlier, right. So, at the peak and the valley, wherever the signs of slopes are changing, you shift it to 0, basically you make it to the upwind scheme, okay, or the basically the constant variation or the constant piecewise within the cell. But whenever you have it is either going up or going down, okay, that means your SU, SD on both the sides of the cell are basically greater than 0. In that case, you have to pick the slope which is lower. So, you take the magnitude of this downwind slope and the upwind slope and see if it is SD is lower than SU, then you pick that. If SU is lower than SD, then you pick that. Okay. For example, look at this case here. Okay. So, you can get the slope, let us say you want to get the slope here. So, you can get the slope from left side, okay. This can be one of the slope, one of the way, okay, or you can also get from this side, okay. So, if you pick it from this side, then it will go like this, right, and as we have discussed earlier, this will lead to creation of overshoot, right. So, what mean mode does is that it looks at the slope from the coming from this side, okay, which is basically I and I minus 1, and then it looks at the slope from I and I plus 1, and then it found that the magnitude of the slope on I and I minus 1 is smaller. So, it picked up this slope, okay, and not this one, not this one, right. Similarly, if you want to pick up for this one, you can for this also you can take from upwind or you take from downwind, okay. In this case the upwind was smaller, so that is why we picked up the upwind one. Okay. In this case the downwind is smaller, right. If you look at this slope and this slope and you found that this slope is smaller, so we picked up this slope, and you can think that if you would have picked the slope like this, okay, coming from this point, then it would have led to the undershoot. Yeah, this will be the undershoot and this will be the overshoot. Okay, if you pick up from the right instead of left. So, what mean mode does is basically it avoids of both the undershoots and overshoots. It looks at the slopes from both the sides, the left of the cell, right of the cell, look at which magnitude of which slope is smaller and pick up that slope. Okay. You remember that you will compare the magnitude, but we pick up the actual slope here. Okay. And yeah, and whenever, so this actually this example that I presented was for the peak or the valley, where you have SD, this is SU and SD. If you multiply this SU SD, then it is less than 0, it is negative, because one is from this side and another is from this side. In this case the value goes to 0, there is no slope here, it goes to the piecewise constant variation in the cell. Okay, you can also formulate this mean mode based on the ratio of upwind and downwind, and this is for C greater than 0. Okay, if C less than 0, then you have to probably do I plus 1 minus I ui by ui minus ui minus 1. Okay. So, as I mentioned earlier that we will be discussing all these formulations for wave speed which is going on the right, C greater than 0. So, based on this ratio of different cell variables, I mean the difference of cell variables from I minus 1 and I plus 1 and I, okay, you can construct the same definition of slope like this. So, for example, this is the slope sigma I, okay, which depends on phi r I, which we call as the limiter. Okay. So, this is the slope and this is the limiter. So, this is the slope limiter. Okay. We will also use the term flux limiter later in a different slightly different context. And then we define the slope limiter, which depends only on this value r. Okay. And this is the mean mode slope, same thing that we discussed earlier, but now we are writing in the form of r. So, which is basically max 0, mean 1 r. So, basically we will take at mean and 1 and r, take the minimum of these two, and then from that and 0 you take the maximum. So, let us say that r is less than 0, okay, that means the slope you are getting from left and slope you are getting from right have different signs like this. Okay. So, then what will happen is that in this case r is less than 0. Okay. So, the phi r will become 0, right, because that will be max of 0 and some negative number, let us call it minus n. So, this will be 0. So, the slope is 0, right, slope is 0 from here. Let us say your r is greater than 1. Okay. So, that means your SU bar, this one is bigger than the SD, okay, and you have to choose the smaller one. So, you should choose this SD, and that is why this phi r becomes 1. You can work out here, okay, because r greater than 1, they have to take the minimum 1 here, you get 1 and they will get this SD, okay, multiplying here 1. Okay. If you have basically r is less than 1, okay, then what will happen, that SU is less than SD, like we discussed earlier, and then phi r will become nothing but r, and then you multiply this sigma I by r s t and it will become SU. So, you are picking the smaller one here also. Yeah. So, this is the same thing, r is less than 0, this is not monotonic, and then the second order creation will create a overshoot over undershoot that we want to avoid. So, this is only at peak or a valley. Okay. So, now so eventually what does this limiter does? If you remember this Gordon-Noyes theorem that we discussed earlier, that any flux scheme or any numerical scheme which is higher than first order will eventually develop, which will not be a TVD scheme if you are using a linear scheme, right. It has to be something called non-linear, and that is what is happening here. Okay. So, we will use this limiter function as a non-linear filter. Okay. So, the value is in the smooth region, it should be near 1. So, this will get full lax band drop. If it is less than 0, then either peak or a valley, then it should go to 0. Okay. And if it is r is very very large and very very small, then it is the discontinuity, then again it goes to the upwind. Okay. Let us look at this behavior. So, let us say you have a cell which has the value of 0, 0, 1, 1 and 1, right. So, let me represent in different way. Okay. So, this is 0 and this is 1. Okay. So, if you look at this value, let us say this is 0, 0 and this is 1. Okay. So, you calculate the slope here. So, r value is basically this is 0 and this is 1. So, r value is 0. So, you will pick the first order in this region, this is plane, it does not matter, because if you look at the flux formulation earlier. So, we had this something called upwind part and plus the correction we had, which was basically coming from I plus half and I minus half. Okay, because this is anyway a smooth plane. So, this will go to 0. So, it does not matter what correction that you are adding here. Okay, so, it will go back to upwind. Once it comes to let us say this portion, okay, which is basically a so, now we are going to basically 0 1 1. Okay. So, now let us say now we have not gone here. So, this is 0 1 and this is 1 and then 1. Okay. So, near the shock it will go to 0, this is 0 0 1 near the discontinuity, and again in the shock this is let us say 1 and 1, this will go to Lax-Van-Draaf, and after the jump it can again go to 0, which is be again the smooth plane. Okay. So, if you look at like this, it has gone 0 here, 0 here and then this is 1 here. So, phi equal to 1. So, within this region, or even if let us say if you want to resolve the shock, and shock is being resolved at many points. Okay. So, at this point left of this or right of this, it can be 0, very close to the shock, the discontinuity, but within the shock it can go to the higher order and it can let you resolve the shock better. Okay, let me show you one example here. Okay. So, again the same problem, we have the Gaussian wave and the square wave. Okay. If you use for example, Lax-Van-Draaf or beam warming, will have these wiggles that we discussed earlier, but if you use a mean mode filter, okay, you see this is slightly dissipative, okay, but all the wiggles are gone. Okay. You can see that all the wiggles are gone here and it is a very nice smooth profile, and it is a basically a TVD reconstruction. It is non-linear because we have this R function which takes the ratio of I minus 1 and I plus 1 I. Okay. So, this is the job of the filter, that it leads to removal of these wiggles, and it can go to second order scheme. So, this is actually a valley here, it is a peak here, and that is why the volume goes to 0 here. There is no second order here, but second order can be applied here in this region. Okay. Here also you have to go to 0 and this region, not this region, so this region and this region, but otherwise you can have the second order and rest of the regions. Again, these are the smooth planes, it does not matter, the phi can go to 0 here, because anyway the correction that you have from the upwind will be 0. There is no difference between I plus 1 minus I. So, let us say this is my I plus 1 and this is I and this is I minus 1, right. So, the difference you take here or difference you take here, they are not contributing. Okay. So, that is why the upwind is good enough here. Okay. But you can see that in the smooth region it can lead to a better prediction. Okay. If you do not use the second order, it will be even bad. If you do not use the second order, let us use the first order scheme, it will become like this, okay, and it will become like this, okay, without the mean mode limiter. Okay. Now, we used the mean mode limiter and we saw that we are picking up the slope which is coming from the upwind or the downwind, and we picking one of these. Okay. But is it the maximum slope that we can pick? Okay. Because we see that once you use a mean mode, still you have some dissipation. Is there a way to get rid of this dissipation or minimize the dissipation, right? So, then the question comes in that we are using the slope and we want to avoid the undershoot and overshoot, and that is why we are picking from the left and the right. But is it the maximum slope that you can pick? Can we go beyond let us say what you are getting the slope from the left or the right and still avoid the undershoot or overshoot? Okay. So, let us look at this. Okay. So, this should be c greater than 0, this is the speed of sound, okay, and this r we have already introduced, okay, and this is the slope formulation. Okay. Now, for second order accuracy, we want that we will have a linear variation here, okay, and you can write in the form of the limiter here. So, this sigma I can be written in terms of phi r I this form, and you will have this slope limiter phi r I. Okay, this is called the slope limiter. Okay, and we want to find out what is the maximum value this slope can take. Okay, can it be limited to only the S d and S u, or it can become bigger than that. Okay. So, there are two constants. So, if you have this is I plus 1 and I minus 1. Okay, there are two constants that it needs to follow in order to stay monotonic, or in order to follow the TBD. One is that the reconstructed value that you are getting. So, you have I, and you will have I plus half, and you have I minus half. Okay. So, look at the downward constant, basically whatever value that you are getting from this reconstructed from I to I plus half, okay, that should not be bigger than what you value have in I plus 1. Okay. Let us say you have this value here and I plus 1 is here. Okay. I think I should make it like this, and this is going like this. Okay. Then when you reconstruct, when it move it forward, then we still violate this, it will even overshoot. Okay. Similar thing will look for the for the upwind condition also. So, whatever value that you are getting on this plane I plus half should be smaller than less than or equal to I plus 1. This is the downward constant. So, use this formula that we have, okay, and then rearrange the variable, this u I plus 1 u I will get cancelled out, and you will get phi r I is less than equal to 2. So, the maximum value of the slope limiter can go to 2. Okay, this is coming from the downwind constant. If you look at the upwind constant here, okay, so the upwind constant is now coming from I minus 1, and this is I plus 1. Okay. So, it's what it is saying that whatever value that you are getting, so this is my I minus half and this is I plus half. Okay. So, whatever value that you are reconstructing at this point, okay, u I minus half, okay, that should be basically bigger than the value that you have at I minus 1. So, from the left cell, that is how it will be monotonic, right. And again, as I mentioned that I am talking about C greater than 0 or A greater than 0. So, now you can write this u I minus half in terms of u I minus sigma, this is my delta x, okay, sigma delta x by 2 sigma is the slope that you have defined earlier, okay, and you use this expression here. So, this is u I minus 1 is equal to less than equal to u I minus whatever value that you have, okay, and then you again rearrange, and you have one side u I plus 1 minus u I and other side u I minus 1. Okay. So, this phi r I will become this value, and which is nothing but your r I. Okay. So, then your phi r I should be less than equal to 2 r I, right. So, we have got two constant, one is the maximum phi r I is equal to 2, okay, this is the max, and the second is that whatever slope that you have, it should be less than equal to 2 r I, right. So, once you basically use all these properties, okay, so this is called the Swebe diagram after a mathematician Swebe. Okay. So, we can actually define what is the TBD region. Okay. So, we have to have basically one is that when r is less than 0, as we discussed earlier, whether it is peak or the valley, okay, it should go to 0, then it becomes upwind. Okay, for r less than 0, whenever there is a mismatch in the slope, we will have phi equal to 0, and for the TBD region, as we discussed earlier, it should be minimum of 2 r and 2. Okay, so this is one boundary and two boundary. So, we will have the diagram which is basically phi r coming from this, and this is basically capped by this 2 r and 2. Okay, and then another thing is that the boundary must pass through basically 1 1, and why is that? Is if you recall, we want it to be the second order in smooth regions. Okay, so, you want it to be the maximum value, right. So, it has to be when the ratio is equal to 1, you can have the limiter function as equal to 1, right. So, then you will get this Swebe diagram. So, Swebe diagram. So, basically you will have one line which is coming like this, which is nothing but phi r equal to r, and what is r here? Ui minus 1 by ui plus 1 minus ui, right. So, this if you put in the expression that we had earlier, you will basically get the beam warming. Okay. Remember, the in the beam warming we are using the upwind slope. Okay. And if you take phi r equal to 1, which we discussed earlier, this is the line that will give you the lax band drop, right. And then we will have the maximum slope, which we discussed, that phi r is equal to 2 r, okay, which is this line. Okay. And finally, we also have that it should not exceed 2, right. This is the 2 axis, right. So, now finally, by combining all these things, so one thing you can see that why the lax band of keeps wiggles is because even in this region you have the value which is equal to 1. I mean, it should go to 0 in this region, but it remains 1. Similarly, if you look at this beam warming, will have value exceeding 2, right. So, we will have the boundary which is coming from this the beam warming, okay, which is passing through 1 1, okay, and then we have the another boundary which is coming from the maximum slope, that can be basically 2 r, and then we will have the maximum value which is 2, and we want to basically have the second order in the maximum places as much as we can. So, this is the lax band drop that we have here. Okay. If you are using the value of equal to 2, it is basically smoothing too much. If you are using equal to 1, it is just doing the right thing. Okay. And in this region, anything which is less than basically r equal less than 0, it should go to 0. Okay. So, this gray region that you see is basically what we call as the TVD region, and you can design any slope, but if it stays in this region, let us say you can design like this or you can design like this, any slope that can stay in this region will have the TVD property, and that will not create undershoot or overshoot. Okay. So, let us look at some other limiters. Okay. So, yeah, this is the same diagram. Well, I will come back to this picture soon. So, we will have another slope called super B slope. Okay. So, as we discussed that we can go to the twice the slope. So, we will have one slope mean mod coming from minimum of SU and 2 SD, okay, and then we will have another one which is twice of the upwind slope and the downwind slope. So, take mean mod of this and mean mod of this, we have seen the definition of mean mod earlier, and then pick the maximum slope of that. So, this is called the super B slope. Okay. It gives very sharp result near the shock, but it has some other problems that we will see later, and this is how the super B slope will look like. Okay. It is not doing only this or it is not doing this. Okay. It is basically you have one slope coming from here, one slope coming from here, but then it looked at basically the double the slope and use this mean mod here and mean mod here and picked up this maximum slope which is look like this. Okay. And here also did the same, and you can see that this is also not developing any undershoot or overshoot. There is no point which is going like this or going like this, right. So, this is the super B limiter, and it is coming from the theory that it has to bound between the 2 r, okay. It cannot exceed 2 r. Okay. Then we have something called the monotonized central limiter or MC limiter as it is called. So, it is the mean mode of the 3. Okay. So, basically 2 SU, 2 SD, and then you have SU plus SD by 2. Okay. So, this is a kind of centered slope as we saw in the From's scheme. Okay. So, it will have the centered slope in the smooth region, but switches to a limited slope near the sharp gradients. Okay. And you can write the same thing in the form of R here, in the form slope limiter here, which will have maximum 0, minimum of 2 r, 1 plus r by 2, which is coming from here, and 2. Okay. And then we will have a limiter called one layer limiter. Okay. And this will have basically r plus mod r by 1 minus mod r, and this is a differentiable function, unlike the all the 3 slopes that we have seen. So, they will go like this or basically go like this. Okay. This is a smooth slope. Okay. So, so all those other like mean mode or super B, even MC will may have the sharp corners, but one layer is a smooth curve. Another property it has is that it treats the compression and expansion symmetrically. So, when if you have the grid coming from left to right, I mean the flow going from left to right or right to left, okay, this will have add the similar dissipation, okay, because it is symmetric. You can put this R instead of 1 by R, you will get this phi R by R. Okay. Yeah, so this is just the comparison of these 4 limiters. So, we have seen the mean mode limiter earlier, it is most dissipative and gives a smooth result. The one layer is not piecewise linear, it is a smooth function, okay, and good for expansion waves. Okay, we will see why it is good for expansion waves. Okay, and then we have this super B limiter, which is very sharp, but it is good for contact, but it is not generally used, because if you give a smooth profile, it will eventually make it sharp. Okay, that is what the super B does. So, it is opposite to what basically the first order solver does. In the first order solver, you have this is the sharp one and it makes it smooth, the super B does the opposite. Okay. And then you have this monotonized central, where it is very popular and it is basically using the maximum gradient that you have, but still I mean it combines the mean mode and the centered slope. Okay. And all these 4 are basically TVD, total variation diminishing. So, will not develop undershoot or overshoot. Let us look at how these slopes look like. Okay. So, this we have already seen, this is your this line, this is the lax band drop and this is the beam warming line. Okay. This is phi r equal to r and this is phi r equal to 1, right. And here we have r, we have phi r, and if you look at the mean mode. So, basically it picks up the minimum one. Okay. So, this is the blue line that we have, this is 0 here, everywhere r less than 0, all these limiters have r at r less than 0, wherever you have a peak or a valley, it goes to the first order. Okay. But whenever you have this r value greater than 0, then the behavior of limiters are different. In the case of mean mode limiter, it is the most aggressive one. Okay. So, it increases just the slope, it picks the downwind or upwind slope, okay, up to 1, and then it goes to maximum value of equal to 1. Then we have this super B limiter, it can go to the maximum value of 2, and it picks the double slope here, this region, okay, and then 1, and then picks this slope here from upwind or downwind. And as I mentioned, we have this one layer limiter, which is smooth, goes like this. Remember, all of these, as you can see, they are all within the TVD region. Okay. And finally, you have this monotonized central region, okay, which picks up the double slope here. So, it is not as smooth as mean mode, and then it can go to the value of 2 maximum, right. So, if you look at read the diagram carefully. So, less than 0, all of them they clip the peak. I have not included one layer here, but yeah, you can have similar conclusion by looking at the plot. So, when r is equal to 1, which is smooth, okay. So, then all 3 values goes to 1 here, okay, all 3 of them has to go 3 1 1, okay. When basically the gradient is basically whatever you get from I plus 1 minus I and I minus 1, okay. This can be, it is 1 by r actually. So, r will be reverse of this for a greater than 0 or c greater than 0, okay. In this case, it just goes to the phi r equal to 1, okay. In the smooth, wherever you have the smooth region, wherever you have the smeared region, okay. So, for example, r equal to 0.5, look at r equal to 0.5 here, okay. So, this is most diffusive, and then we have this, I mean in between you have this one layer, but then we also have MC and it gives you the maximum value of 1. So, that is most sharp. If the value of phi increases, it gives you more sharpness, right. So, this is most aggressive. If you look at the steepening when r equal to 2.0, so this is r equal to 2.0, and you can look at the behavior, compare here. So, this mean mode is just 1, okay, but this goes to for the super B it goes to 2, and you have in between value for one layer and monotonized central. Okay. So, if you look at the behavior in SOC, so the mean mode is smeared, okay, the MC is sharp and super B is very sharp. Okay. If you look at behavior in Gaussian, for example, we have this curve, okay. If you look at this on this curve, So, it clips the peak in the min mode, more dissipation. In monotonic central you have less dissipation, but in this case it actually, if you look at run it for long time, it will become like a square. Okay. So, that is why the super B is typically not used. This is very sharp limiter. Okay. Even the Gaussian wave it treats like a discontinuity. Okay. And this is how the behavior will look like. Okay. So, the same problem that we discussed earlier, it is just being convected with the expression u t plus c u x equal to 0, and this is initial Gaussian and then initial square wave, and you can see the min mode gives you some dissipation. The super B gives the least dissipation, but it is actually converting it slightly into the square wave. Okay. MC is better, it still does little bit squarish, but it also preserves, it is not as dissipative. And if you look at the curve which is the square wave, right. So, you can see that super B is preserving the best. Okay. The min mode is the most dissipative one, and MC is in between, it is a balance of this, right. So, I hope this gives you a picture of how things work. I also want to show you this picture here. Okay. So, what we have, I have plotted here is that what is the value of phi r. Okay. So, if you look at this peak, so at the peak where this r is less than 0, so they all go to 0. Okay. These are the flat regions, okay, nothing is happening here. So, this is basically 0 by 0, right. This, if you look at the r value, this is 0 by 0, because u I plus 1 minus u I on top of u I minus u I minus 1, they are both 0, there is nothing happening here. So, it does not matter, because if you look at the upwind and then you have up high minus f low, this is anyway 0. So, it does not matter if what value you take as phi r. So, we kept it at 0. Okay. And then we have this constant gradient where you have, so it can go to the value of 1. Okay. So, 1 is the value that we have used here in the case of super B, and uh, even MC, it can go to very high value up to 2 for some reason, some point. Okay. But it has to go to 0 at the peak or the valley. Okay. So, you can look at the distribution here. So, the MC actually it goes like this and goes like this. Okay. And this is the 0 value. Okay. If you look at the super B limiter, it goes very high to 2 value, this is how it is going, then dropping very fast and then goes up. Okay. And if you look at the min mod limiter, so the distribution is, so it goes like this. Okay. And then it goes to 0 at the peak at the and then it again maintains the maximum value of 1. And if you look at what happens very close to the shock. Okay. So, you will have value which is 0 here. Okay. And then I mean when this gradient becomes equal to 1, then it goes to the second order. Okay. And this is the same thing for the sweepy diagram that we have seen earlier. Okay. So, this is the comparison of the slope limiters. What we will do in the next class is that we will introduce another concept called flux limiter, which is basically related to the slope limiter concept. So, in that case, we will, instead of talking about how we are reconstructing within the cell, okay, we will discuss this from the point of the view of the flux. So, we have basically f I plus half and f I minus half, okay, and we are constructing this flux. Can we multiply with the limiter called phi? In this case, this is the flux limiter, okay, and which we can make an scheme which is TBD, right. So, that is what we are going to discuss in the next class. Okay, with that I will stop here. Thank you very much.